It's time for another Topic Tuesday. This one will be over fluids, and it'll be our last Topic Tuesday. So one thing we talked about with fluids is density. So that is rho equals m over v, or density is mass divided by volume. So that means that if we're talking about the weight, and it can be the weight of anything, it doesn't have to be a fluid, is mg we know, but that's also then rho vg. You should be able to determine if something will float or sink. So it will float if its density is less than the density of water, and sink if its density is greater. Be careful with your units. The standard physics units are kilograms per meter cubed, whereas chemistry might use grams per cubic centimeter, and they might be cruel, or I might be cruel and give you those units as well. So you might need to convert. Here's an example. You should be able to go through and do something similar. Wrecking balls are super heavy. Specific gravity, that's the ratio of the density of an object to the density of water at 4 degrees Celsius. So the density of water is 1,000 kilograms per cubic meter. Specific gravity, since it's a ratio, has no units. You should be able to calculate pressure, which is the force per unit area, where the force is acting perpendicular to the surface area. Your equation is pressure is force divided by area. The units are pascals, or PA, so 1 Pascal is 1 Newton per square meter. I have a lovely joke about that, if you remember. So here's a pressure example. I'm not going to go through it, but you can look through and figure out that. One thing to note about pressure is that it's the same in every direction in a fluid at a given depth. If it weren't, the fluid would be in motion. If the fluid's not moving, it is at rest, and therefore the pressure on all sides must be equal to keep it static. How does pressure of a liquid vary with depth? So pressures is force over area. So pressure due to fluid of height h for an object at depth h. If we're looking, the force is the weight of the water, which is the area times the height times g times pressure. So rho gh is the pressure. So pressure at equal depths is the same regardless of the various shapes that you might have above your fluid. We're assuming incompressible fluids, which means the density is constant and it doesn't change with depth. This is idealized like pretty much everything else that we do here, but it's true for small amounts of fluid and kind of small ranges of pressure changes. Another example problem, just plugging into rho gh. You should know the difference between atmospheric pressure and gauge pressure. So the pressure of the Earth's atmosphere changes with depth, varies inversely with altitude. At sea level, we have our pressure is 1.013 times 10 to the 5th Newton per square meter, or pascals, which is 1 atmosphere. Gauge pressure then is the pressure over and above atmospheric pressure, kind of like using the tare button on a balance to remove the mass of the weighing container and then seeing what it is. So you should be able to make calculations with atmospheric pressure, gauge pressure, and absolute pressure. So that equation is pressure is atmospheric pressure plus rho gh. There's some different applications that we discussed that hopefully sound familiar to you. The manometer, that was that curved tube with different fluids in it. Suction cups, straws, how straws work, and then the long straw in particular, why we're able to make long straws work. Here's an example with this, where if you put your finger between the top of the straw with fluid in it, and what's the pressure like between your finger and the top of the liquid. It should be less than atmospheric pressure because the bottom of the straw is what's open to the atmosphere there. Pascal's principle you should know about. That says that the pressure applied to a confined fluid increases the pressure throughout by the same amount. So pressure due to some depth or some location, if we push in one spot, it pushes out everywhere. A change in pressures applies to an enclosed fluid is transmitted undiminished to every point in the fluid and to the walls of the container. If you increase the pressure at the top of the fluid, you increase the pressure everywhere, and in fact, you increase the pressure everywhere by the same amount. I think you guys have done some AP problems where somebody's floating in the pool, and so even although they're floating, they're increasing the pressure at the top of the water, and therefore there's an increased pressure at the bottom of the pool as well, and the sides of the pool. Hydraulics, this is using that idea that the pressures should be the same. So a small force can be used to exert a large force by making the area of one piston, the output, larger than the area of the input piston. So the pressure out is equal to the pressure in, which means force out over area out is force in over area in. And you can get a mechanical advantage there. So this is the idea for how we can lift a car. This is showing the same thing again. One thing to note here is you're getting the same amount of workout because on this side you may be putting in a small force and here you get a big force, but on this side you need a big distance to move and on this side it's a small distance. Here's an example of this. Using suction cups in space won't work because suction cups rely on the outside pressure and low pressure inside the suction cup. We talked about buoyancy, that objects in a fluid appear to weigh less than when outside the fluid because we have a buoyant force acting upward. The buoyant force is equal to the weight of the fluid displaced, which is rho GV, where rho is the density of the fluid. Buoyant force caused by the pressure difference between the top and bottom of the object. It acts vertically upward. We talked about Archimedes' principle that states any object completely or partially submerged in a fluid is buoyed up by a force whose magnitude is equal to the weight of the fluid displaced by the object. So buoyant force is the weight of the fluid displaced. The buoyant force on an object or on a body immersed in a fluid is equal to the weight of the fluid displaced by that object. Here's an example, lifting a statue. Another example, determining if something's gold or not. You guys had a test question like that. Floating objects, Archimedes' principle applies to objects that float as well. The issue here is just that the weight of the object is equal to the buoyant force, which is equal to the density of the fluid times the volume times G, but here the volume is only the volume of the object or of the water that the object displaces, or the fluid that the object displaces, which would be less than the total volume of your object. This is what I just said. So for floating object, buoyant force balanced by the force of gravity. And just be careful on if you're talking about, right, these are your weight side and this is your buoyant force side, that you're not mixing things up. Another example with a hydrometer. Example here with plate tectonics. Then we switched gears in this unit and we talked about fluids in motion. So we define streamline flow as the flow or the motion of a fluid in which every particle in the fluid flows or follows the same path past a particular point. We assumed that fluids are moving streamlined, they're incompressible, there's no internal friction. We had the continuity equation, which is A1V1 equals A2V2. And so what happens here is if we have a large area, small velocity. If we have a small area, we have a high velocity. But we still have the same amount of fluid moving through, so this is a conservation of matter law. So the product of the cross-sectional area of a pipe and the fluid speed across that cross-section is constant. So AV equals flow rate equals volume over time. The same amount of fluid entering the tube is equal to the amount exiting the tube. Here's the same thing again. And again. And an example, figuring out how many capillaries there are. Another example with air ducts. And then we talked about Bernoulli's equation. So Bernoulli's is a consequence of conservation of energy. As a fluid moves through a pipe of varying cross-section and elevation, the pressure changes. We can derive it. Don't worry about deriving it. There's some more deriving it. Here's the bottom piece. Here is the actual equation that our pressure at one point times rho GH1 plus rho V1 squared over 2 is equal to our pressure at the second place plus rho GH2 plus rho V2 squared over 2. So what this means, if height is constant, a higher velocity means less pressure. If pressure increases, velocity is going to decrease. So this is what makes planes fly, what makes arteries collapse if they're clogged. So we're seeing that this expression is constant at every point. So another way of thinking of it is a law of conservation of energy. So continuity, conservation of matter or mass, Bernoulli's equation, conservation of energy. Here's an example you can look through. Terselli's then is if we have a specific leaky tower type problem, and it simplifies to square root 2gh. I wouldn't worry about it. I just use Bernoulli's and cancel things out. Here's some pictures of Bernoulli's. Kind of that weird idea that high velocity means low pressure. We kind of want to think the opposite is true, but it's not. Applications are like perfume bottles or depending on different kind of aerosol type things, ping pongs, airplane wings. We talked about a Venturi tube, ways to measure pressure. You should know streamlined, laminar, terms turbulent, flow is irregular, viscosity, how much internal friction we have. We're assuming ideal fluids, which means that it's non-viscous, it's incompressible. The fluid motion is steady, there's no turbulence. I've got some various examples here I'm not going to go through, but if you have any questions with these, please contact me. Learning targets, I'll post those as well. And then the last thing I want to do in this video is look at the AP equation sheet. So let's zoom in a little. Relevant equations for this section. You should have the atmospheric pressure we see here, and they're rounding to 1 times 10 to the 5th instead of 1.013. Then if we scroll, we're on to the second page of equations, and we're looking at fluid mechanics. So we see our equation for density, for pressure, for absolute pressure with atmospheric and gauge pressure, our buoyant force equation, continuity, and Bernoulli. So that is fluids in just under 13 minutes. Let me know if you have any questions.